Hello guys, welcome to our last topic for our online class. So in this topic we're going to discuss about electric field. So what is electric field? It is defined as the electric force per unit charge, and the direction of the field is taken to be the direction of the force it would exert on positive test charge. The electric field is radially outward from a positively charged point and radially inward from a negatively charged point. So in this picture, this is actually called a dipole with a positive and negative charge. So if the charge point is a positive, the lines would go outwards. Okay, so in a single charge, if it's just positive, it will just go something like that. It will not actually curve. But if it's paired with another charge which is negative, it will create this curved lines, okay, making it as a dipole. So positively charged point going outward, okay, outward, and negatively charged going inward, okay. So if a charge or a point charge like this one goes near to the like a large compared to a small one. So the force, the direction of the force, we all know that positive or like charges repels. So the direction of the force is actually tangent to the curve of the electric field lines. So this is actually called electric field lines. Okay. So when it goes near, the force actually increases. Okay. So as you can see, the line here is much shorter compared to this one because it's near to the biggest positive charge point. Therefore, it will have a greater force. And again, the force is tangent to the curve. So, say you have a charge here and it goes near to the positive, so this one will repulse, and the force will actually be greater. So, what is an electric charge? It is a physical property of matter that causes it to experience force when placed in electromagnetic field. Okay, there are two types of electric charge, which is the negative, which is commonly known as the electrons, and positive, which is the proton. An object with an absence of net charge or without charge, either a positive or negative, it's actually referred as a neutral charge or just neutral. So what is the formula for electric field? It is actually equals to electric field strength, okay, or electric field equals to E equal to force over the charge. So our E here is electric field strength, which has a unit of Newton per Coulomb, and F is electric force, which is Newton, and Q is electric charge, which has a unit of Coulomb. On the other hand, applying Coulomb's law and electric force, we have this formula. Force equals to the Coulomb's constant times charge 1 times charge 2 divided by the distance squared. Okay, this looks familiar to you, of course. This formula is also used with the universal gravitation. You might ask which person who first derived this formula. Of course, the person who derived this formula is Newton. So it was like 100 years later when Coulomb derived this formula. Okay, so You will see the difference later. I'll be showing a video to further explain this difference. So F here is the electric force, as same with our electric field strength equation, E equals to F over Q. And then K is the Coulomb's constant, which is equal to 8.99 times 10 to the 9 Newton times meter squared per Coulomb squared. And Q is electric charges, so two charges, Q1 and Q2. And the unit is in Coulomb. And R is the distance between two charged objects, which has a unit of meter. So correlating the two, again, you can actually rewrite this equation to correlate with this equation. Okay, so we can rewrite this one. So if two charges are like two apart to each other, let's say this charge Q1 is isolated. So if it is isolated and charge 2 is very small, okay, we can actually derive this equation. So replacing this to this, giving us E equals to the Coulomb's constant times Q1 over the distance of this two charge squared. So again, this one is very small compared to this one. Let's say charge 1 is this big, and then the charge 1 is very small, something like this one. Okay, or we can rewrite this formula as this one without the number on it.
First, we noticed that there was such a thing as electric charge. The easiest demonstration of this involves rubbing a balloon on your hair and seeing how the balloon will then attract your hair by some mysterious force. Two balloons that have been rubbed on your hair will strangely push each other away. This occurs because of electric charge, which is displaced by the rubbing together of these materials. The hair becomes positively charged and the balloons become negatively charged, which is terminology developed by Benjamin Franklin. Opposite charges will attract one another, which is why your hair sticks to the balloon, and like charges repel, which is why the two balloons push each other away. This property of electric charge is carried by certain subatomic particles. The most common of these are protons, which are positively charged, and electrons, which are negatively charged. Along with neutrons, these make up all the atoms in the universe. As it happens, electrons, which are the essence of electricity, are easily transferable, and it is the transfer of electrons, in this case from your hair to the balloon, that generates electric charge in previously neutral materials. Each electron carries with it the fundamental charge, which is 1.6 times 10 to the negative 19 coulombs. This magnitude is negative for the electron and positive for the proton. All substances will therefore have a charge that is some multiple of this amount. That is to say, electric charge is quantized. We can categorize substances by their ability to transfer electric charge. A substance that can easily transfer electric charge is a conductor. One that can't is an insulator. Opposite charges attract one another because of the electric force. This is outlined in Coulomb's law, which states that the magnitude of the electric force between two objects is equal to the Coulomb constant times the charge on one object times the charge on the other, divided by the square of the distance between them. Remarkably, this is essentially identical to Newton's law of universal gravitation, the only differences being that the electric force can be attractive or repulsive, depending on the signs of these terms, and the resulting sign on the force, while gravity is always attractive. Also, it is interesting to note that Coulomb's constant is 20 orders of magnitude greater than the gravitational constant, illustrating the discrepancy in the strength of the two forces. This law also tells us that the electric force between two objects increases as charge increases and decreases as the distance between them increases. If more than two charges are present, vector addition must be done to find out the net force upon any particle in the system. Just as a gravitational field is what allows the gravitational force to propagate, it is an electric field that allows the electric force to propagate. However, as we said, the electric force is much stronger than gravity. This is evidenced by the fact that the repulsion between particles in your feet and particles in the ground is more than strong enough to keep you from plummeting towards the center of the Earth. We can also use a cheap refrigerator magnet to keep a piece of paper on the fridge against the gravitational pull of the entire planet. Any charged object will manifest an electric field around itself, and if another charged object enters this field, interactions will occur. The strength of an electric field generated by a point charge is equal to the Coulomb constant times the charge on the object producing the field, divided by the square of the distance between this object and whatever it is acting on. One way we depict electric fields is by drawing electric field lines, which generally point towards negative charges and away from positive charges, and do not cross. These don't really exist, but they are a convenient way to analyze the direction of a field at any point in space, like the field produced by these two oppositely charged particles, which we can call an electric dipole. The more densely packed the field lines are in a particular region, the greater the strength of the field. Lines like these can be especially useful if many particles are producing the field.
Okay, so that ends our discussion about electric field. So if you have any questions or comment, just leave it below, and I hope you have a great time. Thank you.